All right, good afternoon, everyone. Sorry for a few minutes late for the setting of the Zoom. Again, I just want to mention that today is gonna be our last lecture in the semester. But before we start, I still want to remind everyone that if you haven't started doing homework 5, please just start right now. And please try to fully leverage the office hours. We got office hour every weekday. Don't try to rush in Friday. I've heard some complaint saying that there are too many people on office hours on Friday. Well, I'll say where our office hours are pretty empty from Monday to Thursday, right? So if you start early, and we can try our best to help you. And because after this week, we will not be able to give any office hours because the examination week, right? Our TMs need to take their exams as well. Okay. So any question regarding I think the remaining homework assignments and the final project things? Any concern? Seems everyone is confident for the last homework. Okay, great. So yeah, today we're gonna finish the introduction of the Gaussian process regression. Then we'll give a quick retrospect about what we have discussed throughout the semester to give you a systematic idea about what we have discussed this class, and hopefully can give you some kind of sense if you in the future want to do something related to probabilistic machine learning, and then hopefully our class will give you a good reference. Okay, so continue with the last lecture. We mentioned that Gaussian process regression is another type of very widely used machine learning models. So more rigorous speaking, it belongs to the so-called Bayesian nonparametrics. So Bayesian nonparametrics is a huge branch. What we can view as a branch of the statistics and computational technique. It was like a very hot topic maybe a few years ago. Until recently, it was like superseded by deep neural nets. But Bayesian nonparametrics at sea, they have their own advantages. They are very elegant in terms of mathematics, and also they are very powerful. But the problems for Bayesian nonparametrics that is very hard to learn, especially you want to. Sometimes even it's hard for you to understand the model itself because it often associated with random processes, and the computation also is very expensive. So I'd imagine that in the future, if there's some kind of general tool or library like TensorFlow or PyTorch have been developed for Bayesian nonparametrics, it can be popular again. So okay, so Gaussian process is one kind of like representative example for Bayesian nonparametrics, and right now it still have a very wide applications in practice. So we're going to talk about Gaussian process regression. So basically, we want to use Gaussian process regression to learn some latent function from data, right? So we can assume your function has n d-dimensional input and it is continuous function, right? The idea of the Gaussian process regression is to construct a prior over functions, right? So this sounds a little bit weird at the first sight. However, if you know the definition of the random processes is actually very natural, right? So I just briefly mentioned the concept again. So we know the random variable. So for any random variable, we know that essentially it's not some value, it's a mapping. Right? So it maps some sample space, which is associated with some probability measure, to some real value space. Like for convenience, I just assume it's just R, right? It's possible to be R to D, whatever. Right? So random variable essentially is a function. It's a function. Right? You can map any sample in some probabilistic system to some real value. The reason people make such kind of additional mapping is try to calculate and describe everything in the real space, because everyone will be familiar with that. If you talk about the probability system, it can be applied to anything, right? It can be atoms, it can be gamblings, it can be weathers, whatever, right? But if you map them to a real space, then it becomes a uniform abstract space, and it's easy to study. That's the motivation people invent or develop this concept called random variable. And when we talk about a continuous random variable, we usually mean the mapped value of random variable is continuous value, right? So, and then naturally, we would like to consider, like, why should we just map a sample like this? This should be associated with a probabilistic space. That means you have a sample space. You got a even space, which is sigma algebra, and also you have a and you have a probabilistic measure, right? So you can basically view this guy as like even set, and P is a probability measure each even to a probability. Like, don't worry about it, just to give you some concept. You don't need to memorize that. So, so people would naturally ask, like, why should we map this random sample to a real value, right? What if I map this random sample to a function? So basically, the domain, what if the domain switch to a functional space? If you can define such kind of mapping, like let us denote by fx, no? If we define each mapped function each mapped value of this x is a function, then x is called a random process. That's the definition. Nothing special. And we know that when we talk about function, essentially can be indexed. The function value can be indexed by some input, right? For convenience, we might just use a t to index the value, right? Each input, particular input t, it corresponds to a function value. So people, when they write down the random process, conveniently, they're going to write it as a mapping of both the original random samples from original probability space and some input of the function. So this is the definition of random process. So you can imagine that to sample or to construct the prior over functions, I can use any random process I want, right? And some random process will give you just discrete functions. Some random process will give you continuous functions, right? And why should we use Gaussian process? The reasons is just because it's simple and convenient. No other reasons, right? So, but here I want to just give you a more concrete view of the random process, and we'll proceed to the definition of Gaussian process. Right? So a random process can be viewed as a function of two variables. Right? This omega comes from the outcome or the sample of the random experiment. We know that this omega comes from some probabilistic system, right? And this t actually index the input of your mapped functions. Okay? So if you look at this mapping, like mapping both the function input and also the sample. Right? If we fix t, right? Oh, by the way, if we fix omega, if we fix omega, see omega 1, it corresponds to one particular function, right? If we fix omega to omega 2, it corresponds to another function. Right? So you can see that different omega correspond to different function curves. Right? So that explains why we can have some randomness over the function space, because omega itself has randomness. It comes from some probability system, like you draw on a coin or you throw a dart, whatever, right? You have some probability measurement over omega, and omega is mapped to some function curve. So that function curve has some randomness. That's where this random function comes from. However, if you fix a particular function input t, right? Like fix t. So now if you evaluate your x at this given t, like t1, with different omega, this corresponds to a random variable, right? It just corresponds to a particular value, which usually is real value. So you can view, like for any fixed t, right? The value of the mapped function x at t is a particular random variable. So now we have like two views. First, if you don't fix t, you just look at the whole function curve as a whole thing, right? And when you vary omega, it corresponds to different curves. And because omega itself is outcomes of some random experiments, itself has the whole function curve has some randomness. Right? On the other hand, if you just fix some particular input t, right? Here or here, right? And then you're looking at this random process evaluated at t. Of course, when you vary omega, it corresponds to different value. And that value is also associated with some randomness because omega is random. Does it make sense?
So this is why we have three parameters. What's the difference between those and?
Okay, that's a very good question. So if you want to give a more comprehensive definition of probability system, you have to introduce three elements in a system. One is called a sample space, omega. One is called we can call it even space. And third is called probability measure. So your small omega is some element in this whole sample space. You can view like, okay, if you do some random experiment, what is all possible outcomes of your random experiment? That is the big omega. And the B here, we call it even set. Just means what are all possible events which we believe we should assign probability in this system. Like suppose your random experiment is just throw a dice, right? Then you can define the set of events you believe you are interested to give the probability measurement. Like my first event is my dice is 6. Second event is my dice is less than 2. Third event is my dice point is between 1 and 3. You can define whatever set of events you want. Okay. And then the third guy is called measurable function or probability measure function, which is mapping between the events to some value in 0 and 1. So basically, it gives you the probability measure over each event. Does it make sense? So basically, if you want to make sure your even set is a valid even set, is a consistent even set, you have to assume some properties over this even set definition. And mathematically speaking, it's really called sigma algebra. It cannot be arbitrary set. Arbitrary set. If it be arbitrary set, there will be some very well-known paradox to tell you you can assign some positive probability to some impossible event. So you have to assume some property over your even set, which is called sigma algebra. And if you want to define a valid random variable, you also have some restriction about this mapping. Like it's called inverse image must belong to the sigma algebra. But this is nothing we want to discuss in the lecture. We just want to give you the sense about random process and how do you more comfortably review the random process rather than be confused. Does it make sense? Okay. So now, as we mentioned, right? So in theory, random process actually is a way to generate random functions, right? You actually have a lot of choices to assign a prior over functions, right? And why should we use Gaussian process? As we just mentioned, it is convenient and it's simple. So let's look at the definition of random process, Gaussian process. So Gaussian process is a type of random process such that if you look at every finite collection of the random variables, meaning that the whole function curves are sampled from a Gaussian process, right? If you can pick up arbitrary finite set of function values, then this set of function values will follow a multivariate Gaussian distribution. And this is called Gaussian process. So basically it says if your random process a Gaussian process, that means you can pick up arbitrary finite values of your sample function curve. And those finite set of values must jointly follow a Gaussian distribution. It's called Gaussian process. Does it make sense? So, and when we talk about a multivariate Gaussian distribution, we need to consider what's the mean, what's the covariance matrix, right? Because to define a Gaussian distribution, we need to know what is mean, what is covariance matrix, right? So look at the Gaussian process, right? If we assign a Gaussian process prior over our target function f, right? Then if you are given any finite set of inputs, so x1 to xn, and we know the corresponding function values at this n inputs, denoted here, will follow a multivariate Gaussian distribution. And the mean of this Gaussian distribution is often chosen as 0, but you can define a mean function. Right? Mean function usually is a deterministic function. You can assume, okay, the mean function is a sine function or whatever function. But if you don't have any prior knowledge about this mean function, you can simply set it 0. And then what's the covariance? So the covariance is defined as a matrix where each matrix element is computed by the covariance function. So if you look at this covariance matrix, we see that the element at 1, 1, right? Row 1, column 1 is a covariance function between x1 and x1. And at 1, 2 is covariance function between x1 and x2. And until like at any position mn, right? The element in the covariance matrix is a covariance function between xm and xn. So you can see that actually each element in your covariance matrix is determined by a function, by the function of the corresponding inputs. So we call it covariance function. And what kind of covariance function do we use? We often choose the so-called kernel function. So if we take a look at here, right? So we know that sigma ij is the covariance between f xi, f xj, right? That's the definition. Okay. And we calculate this covariance by using a kernel function. The kernel function itself is actually a function of the inputs, xi and xj. So here I'll give you an example of kernel function. A very common use kernel function is called RBF kernel. So RBF kernel is computed as this exponential. It's very similar to a Gaussian density, right? Except that we don't need to explicitly write down the normalizer, right? And tau here is called length skew. It's kind of a parameter of the kernel function. So we often use RBF kernel to compute the function between, sorry, this is xi and xg, between xi and xg as a covariance between the corresponding function values, namely the function evaluated at xi and xj. So does it reflect? So first, I want to give you a sense. The kernel function usually measures kind of similarity between the inputs. Right? So if you look at this, if xi and xj are the same, the kernel function becomes a maximum, right? So now, if we define the covariance between the function outputs as the similarity of their inputs, what does it imply? We define our covariance of any two function outputs as a kernel function of their corresponding inputs. As we just discussed, the kernel function measures similarity of the input. So what kind of implication can you get out of it? Yeah, correlation, right? Covariance means correlation. So if you look at function, right? If you look at function, we know that the closer the two inputs, the closer the function outputs, right? If this function is a continuous function, right? So we know that, okay, if this is x1, x2, if x2 goes to x1, then function value kind of overlap, right? Kind of overlap. So the Gaussian process prior actually expresses this kind of idea in a statistical perspective. So basically, it says, okay, the more similar or closer of your two inputs, the stronger the covariance or correlation between the function outputs. Right? We're talking about a random function. We can now say, okay, there must be something, right? They have some randomness. However, we're going to still assume if two inputs are close, then their corresponding function values should be more correlated, have larger covariance. Does it make sense? Right. So that's the major idea of the Gaussian process prior. So we use covariance function or kernel function to enforce the fact that enforce our modern assumption that the closer the input, the more correlated the corresponding function outputs. So you can view it as a way to define the function smoothness in a probabilistic context. Right? Again, because we're not modeling determinist function, those functions are randomness. So we must express such kind of smoothness in some kind of probabilistic language. Right? So we can say, okay, these two inputs are very close, right? But the function values, they are random variables. They can jump, right? They can jump here and they can jump here. Just tell, okay, if these two inputs are close, then when this guy jump, this guy should be jump as well. When this guy decrease, this guy should be decreased as well. Right? In this way, you can actually constrain them to be statistically kind of smooth.
So both x and fx are random variables?
No, x is not random. Fx is random variables. Yeah. We're talking about random function, right? Every value of this on this function curve is random, but x is just input space. We index function value, function output by the input. Okay. Any question regarding this intuition? Mm-hmm.
Scenario that you just described implies that for a fixed number of inputs,
yeah.
But what about f seen as a whole?
Yeah, that's a very good question. Actually, there's no accurate way to do that. You can imagine, okay, if you are God, there's some very powerful machine can sample this infinite number of function values in this whole input space, right?
So just find a number.
Yeah. So in practice, if you want to get those curves, I will tell you how to get this. like do some line space, even space over the points to sample a joint Gaussian distribution. That's it.
And the reason that we are going to use RBF data is because that it is more sensitive to similarity.
No.
It's just
You-
inner product.
Yeah, exactly. You can use inner product. You can use xi transpose xg. There are like variety choices of the kernel functions, and use RBF kernel. Simply because RBF kernel implies that your function is like infinitely differentiable. So there's some kind of a nice and insightful connections between the kernel function and the function and the property of your sample random functions. Like if you use RBF kernel, it just implies your sample random function is infinitely differentiable. And sometimes people found this is good enough, but in other cases, people found that this is too ideal, too simpler. You are able to sample functions which are not infinitely differentiable. I just want you to twice differentiable. Then we should switch to another kernel, like material kernel with degree of 3/2. So there are a lot of choices of kernels, and different kernels actually corresponds to different properties of functions. But if you want to simulate like a Gaussian process, right? There's no exact way of doing that. You have to do some kind of discretization. Right? You discretize this input domain into many, many small points. Then you calculate, you use a multivariate Gaussian distribution to sample it, and then just do interpolation. Yeah. Any other questions regarding the idea? This is we're not going to talk about, because Gaussian process itself is a very big branch. There is a book, a thick book called Gaussian Process for Machine Learning. It's free. You can download it for free. If you want to really study it in depth, you can take a look at that book. But here we want to deliver the most critical or most important idea intuition of Gaussian process. And many people they got confused about Gaussian process because they do not aware this underlying viewpoint and intuition. Okay. So yeah, as we just discussed, right? There are numerous ways to define your kernel function, and different kernel functions define different ways to measure the similarity, right? And we know that how much time your function can be differentiated is actually reflecting the smoothness property, right? So, so now, suppose I have constructed such a Gaussian process prior. That means I have specify the mean function, which is 0, and then I have chosen a specific kernel function to measure how statistically function values are similar according to their inputs. And then how do we use this prior to connect to the data and then do the inference of the function given the data, right? That's our goal. We want to learn function from data, right? So in practice, we will never need to sample the whole function because the training data are always finite. Okay. So given the training data, we can consider how to construct our probabilistic model using Gaussian process prior to sample the observed function outputs. Okay. So the idea is pretty simple, right? We can first sample the function values at those big N training inputs, right? So according to the definition of the Gaussian process, we know this N function values must form a multivariate Gaussian distribution. So the mean is mean function, which is assumed to be 0, and the covariance matrix is computed by the kernel function. Right? That means we just need to calculate the finite prior distribution over the function values evaluated as finite training inputs. Right? We never need to really compute the prior density of the whole function curve. Right? And then given the function values f, we can use any model to sample the observed outputs. Right? So if we consider our task is to do regression, that means our observation is continuous, right? Then we often use the choice, the Gaussian likelihood. So basically, the Gaussian likelihood means that, okay, given this ground truth function value sample from the prior, the output, the actual observed output is corrupted by some Gaussian white noise, where noise variance is sigma squared.
So then we are doing just regression.
Mhm.
Our sample space for the function are just parameterized by given theta, and our functions are just linear functions.
Linear functions.
And think of that as a simple example of this.
So basically, when we model it, right, conceptually, we consider our probabilistic modeling procedure will be, okay, we'll first sample the whole function curve, right? And given the function curve, we sample the observed output as some finite input, right? However, in practice, because to generate the finite observations, we only need the finite set of function values. And that finite set of function values will follow multivariate Gaussian distribution. So you never need to really calculate the prior distribution over the whole function curve. Or, yeah.
I was trying to connect these to just simple case. You know, when we can see that when we are choosing just a parameter, then we are assigning the function of that parameters. It means that somehow we are putting the file and just
Okay.
which is known by parameterization. So if we get back to that situation, then this is similar to that, because what you are doing, you are putting file over F, but here F can be very complicated, and we are not able to parameterize it. So we are dealing with each point separately.
Yes. Yes, exactly. Exactly. That's where the flexibility of Gaussian process comes from. You don't really assume the parameterization of F. What you need to just assume, okay, they are correlated in that way. The correlation itself, we just model correlation essentially through the kernel function. Another question? Okay. The regression process is that, okay, you're given this n pairs of the training input and output, right? How do you infer the posterior distribution about the function? But when we say the posterior distribution function, we just want to say, okay, if you are given a new input, can you compute the posterior distribution of this function value after a new input, given the training data? That's our goal. Does it make sense? What's your question? F is a function evaluated at this training inputs. Yeah. So F, this bolded F is actually F x1 to F xn. Yeah. Question? Okay, yeah, let us continue until we see everything, and then you might feel a little bit more comfortable. Okay, so now we have a prior, right? We have the likelihood. We can write down our joint probability distribution over, the function values at those training inputs, and this is observations, right? So this is a prior over the finite function values. although the whole function itself has a Gaussian process prior, as we just mentioned, you never need to really write down the joint distribution of function curve because we don't need it. Right? What we need is actually the joint distribution of these finite function values at this n-training input, right? Because the observation will be generated based on this finite function values. Right? And as we mentioned, according to the Gaussian process property, then this finite function values f, right, will be sampled from a multivariate Gaussian distribution, and the covariance matrix is determined by the kernel matrix, right? Kernel function. And then given the function values, you sample the noisy observations from this Gaussian noise model, and you can see that our model contains two parameters. One is called noise variance, right? This is something we don't know. The other is actually the parameters inside the kernel function. Okay. So just mention that you have a lot of choices of kernel functions. Like one popular choice could be the RBF, which is correspond to 1 exp to the power 1 over tau xi minus xj square, and you take minus sign from here. So this tau is called length skew. It's a kernel parameter. You don't know that. Right? You want to estimate from data as well. Right? So then the learning problem is to estimate what are the noise variance and kernel parameters. So, of course, if you want to keep this latent function values f, right, you want to jointly estimate the posterior distribution of f as well. Right? But here, a more convenient approach will be okay, because the prior is Gaussian, right? The prior is Gaussian, the likelihood is Gaussian. Why not we just marginalize Gaussian? It's very simple. If you marginalize Gaussian, we can get the marginal distribution of the observed data given the input and given the model parameters, which is another Gaussian, where the covariance is actually the kernel or covariance kernel matrix plus this diagonal matrix multiplied by the sigma square I. And then we can simply learn the parameters theta, right? Namely the parameters inside this kernel function and the noise variance by maximizing this guy. That's it. That's how we learn the Gaussian process regression. It's pretty straightforward, right? Any questions so far? Maximize this guy with respect to theta, right? Theta includes the noise variance and any kernel parameters in your kernel function. If you use RBF, then it corresponds to tau here, right? It can be any other kernel parameters. Right? So just maximize this marginal likelihood with respect to the parameters. Of course, in practice, you're going to take a logarithm, right? And maximize the log marginal likelihood. Yeah, that's a good question. We're going to talk about in a minute. Okay. So here we just want to introduce a little bit more information about kernel. If you have taken my machine learning class before, you have seen this content, so please bear with me. So we know that our covariance function, our covariance matrix at an arbitrary set of inputs is computed by the kernel function, right? But covariance must be a positive definite, right? So that means you must have some property to have a valid kernel function must be some must have some property. This property is called semi-positive definite. So so that means not every function which has two inputs can be viewed as a valid kernel function. It must ensure that if you use that kernel function to compute a set of inputs to get this kernel matrix, it must always be semi-positive definite. Yeah, that's a good question. But in math, people will relax it a little bit. Just assume it's a positive semi-definite. And if you want to compute that, it just means a deteriorate Gaussian distribution. You have still a way to compute that. Well, the density won't be. You cannot take the inverse. You have to do some pseudo inverses in that. But in general, yeah, you're right. So in practice, you do want it to be positive definite. But when we talk about theory, we just want it to be a semi-positive definite. So what kind of functions are valid kernel functions? Here, just to give you a commonly used list. First, inner product. Someone has mentioned that a moment ago, right? So this kernel is called linear kernel. And then if you do the inner product, then take some power of degree d, and d is not necessary to be integers. It can be continuous values. This is called polynomial kernel. And the polynomial up to degree d is that, okay, you plus this integral by some constant c, positive constant c, and take power of d. And it's called polynomial kernel up to degree d. And here is the RBF kernel, like we just mentioned. And sometimes you want to model the periodicity properties inside the function. Then there's a property kernel called a periodic kernel, and also have matron kernel and so on. So there's a open source book. It's called the Kernel Cookbook. You see that they kind of list nearly all the common used kernels, right? And and kernel function has a nice properties. So each kernel function corresponds to some kind of feature mapping. And this feature mapping is really nonlinear feature mapping, as it can be very high dimensional. So for any valid kernel function K, there exists some feature mapping psi, which maps the original feature vector, which is kind of relatively low dimensional, to a very high dimensional feature vector. And this mapped dimension D usually is far bigger than K. And for some kernels, this mapped dimension is infinite. So the benefit of kernel function is that, okay, if I compute a kernel function, right, I just fit x1, x2 in our original feature space to K, I can compute it, right? But the result is equivalent to first mapping these two input vector into a very high dimensional space, then to the inner product. That's why kernel function is very popular, and people call it, for nonlinear regression, people call it kernel tree. Why? Because if I want to do a nonlinear feature mapping, but I don't want to explicitly compute it because that's really costly. Sometimes it's infeasible if your feature mapping is infinite dimensional. Right? I can just apply kernel function, so I can avoid the explicit feature mapping and inner product, but still compute their dot product result. So kernel function is a cheap way to compute the inner product between the high dimensional feature vectors. So from this view of kernel function, actually, Gaussian process regression can give us an alternative view. You can view it as a generalized linear models. We have discussed before, right? So how can we see that? Suppose we choose our kernel function xi and xj, right? So suppose it's RBF or whatever. Right? If it's RBF, the corresponding feature mapping psi is infinite dimensional. Right? But whatever, let us assume that we're able to write down that psi. Right? So given this n training points, right? Training inputs and training outputs, let us consider this model. So we're going to first introduce a V vector. This V vector has the same dimension as the mapped feature space with this feature mapping psi. Even it's infinite dimensional, let us assume, okay, this is infinite dimensional with vector W, right? We sample W from the standard Gaussian distribution, and then for each observation output yn, we sample yn from a Gaussian model where the mean is this inner product. That is the weight inner product with the mapped feature vector of xn by psi. And of course, the variance noise is still sigma squared, right? Now I want to claim that this model is equivalent to the Gaussian process regression model we just mentioned. Okay. That means if you marginalize W, right, you can recover this guy, right? Any question? I think everyone has got this point, right? So if you marginalize W, you actually, in your covariance matrix, every element will be psi xm transpose psi xn, right? So which is essentially the k xm xn. So you cover the kernel matrix. So the other word, we can always view a Gaussian process regression model as a linear regression model, but we use some non-trivial high-dimensional feature mapping first. Okay. So in this way, you can build up connection to neural network. Okay. Remember neural network, we mentioned that you got a neural network X, right? You have a bunch of complicated transformation, blah, 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 until you got the prediction, right? But in the last layer, we assume the output only is obtained from some linear transformation. So that means your neural network output can always be viewed as some vector, weight vector W transposed with some feature mapping. Right? This feature mapping can be viewed as, you know, the output of second last layer. Right?
And we think GP Gaussian process is a Bayesian neural network.
Yeah. Yeah, we're going to point out their connection. They have a very strong connection. But here, I would just want to unify the view, right? If you write down the output of your neural network in this way, right? It is always the weight, linear combination of the weight in the last layer with the output of the second last layer, right? This is the output of the second last layer. Okay? So you have this structure. If you assign a Gaussian prior over the weights in the last layer, right? You end up with the same modeling structure, right? And the only difference is that, okay, now your kernel function is computed through the neural network feature mapping. It's a finite feature mapping. And this is actually, this view is very useful. It's very, very useful. And also convenient to understand many properties of Gaussian process. For example, the derivative of Gaussian process is still Gaussian process. Okay, so now we have introduced all the key concepts necessary to learn the Gaussian process. We're going to talk about training and prediction. So as we mentioned, right, when we build up the Gaussian process model for a training set, we can write down the marginal distribution of your observed output given the input, which is still a multivariate Gaussian distribution. We can maximize the log marginal likelihood with respect to the parameters, which include noise variance and the kernel parameters. Right? This is a training. But how do we make a prediction? Actually, Gaussian process is so popular. One possible reason is that making a prediction is very, very simple. It is a conditional Gaussian. Why? Because according to definition of Gaussian process, right, your function value at any new input and your function value at all the training input will follow multivariate Gaussian distribution, right? It will be a multivariate Gaussian distribution. 0, and this is a kernel matrix, right? So now, if we replace this guy with your observed output, we know that this is essentially just a linear combination, right? It's just a summation of your training function values plus some standard Gaussian y naughts, right? So that means f star, fx star, and y will also follow a multivariate Gaussian distribution. And you can write down the covariance matrix in this block form. And for x, the prediction at x star, the covariance is just the kernel function, right? And for covariance of y, it's just this part, right? And for cross covariance between x star, fx star, and y, it's just the kernel function between x star and the training input big X, right? And this guy is just a this guy's transform. Does it make sense? And then, if you want to compute the posterior distribution or predictive distribution fx star given y, how can we do that?
Even from now, everything is known, but the f of s star. So and for the rest of they are fixed, so we can just compute the conditional probability distribution and sample products.
Yeah. You just apply the formula of conditional Gaussian to get the posterior mean and the variance. That's it.
But I have one question. What if we have more than one given point to there's two ways to think about it. Just one by one, or then we compute the prediction. And the first one use it to predict the second one. Which one is better?
That's a very good question. If you have a bunch of points to predict, right, x star 1 to x star m, right? Of course, the ideal way is that you compute the conditional Gaussian of this m predictions, right? And then the benefit is that you not only get the predictive mean, you also get predicted covariance matrix over this m predictions, right? But in practice, people usually don't want to compute the whole predict covariance matrix over like 10,000 test points. So they just do it one by one. Any question?
So what's the difference between x star and x begins?
X star and x ends. So big X is actually all the training inputs. So you got x1 to x begin. X star is some testing input, which you don't know the function value, you want to predict it. Right? But according to the definition of Gaussian process prior, right, your fx star and all your function value at the training inputs, they will jointly follow multivariate Gaussian distribution. Right? That means you can use conditional Gaussian distribution to compute the distribution of fx star given fx1, fx2, and fxn. That's why people are in favor of Gaussian process, because it's so convenient. The predicted distribution is just a Gaussian. It's a conditional Gaussian. Does it make sense? Right? If you feel uncomfortable, look at the multivariate Gaussian distribution, the definition, right? And you got some analytical formula to compute the conditional mean, conditional covariance. You don't need to worry about anything else. You don't need to make any approximations.
This one is for classification, yes?
No, it's not for classification. It's for regression. Right? Fx star is a continuous value. It's a real value. And then you can view like, okay, your observations about x1, x2 to xn are all continuous values. Any other question? Okay. So Now, if you if you use this formula, right? This is just apply the conditional Gaussian formula to compute the predictive distribution for any new input x star, right? So this just apply the formula by looking at this block structure, right? I don't want to show how to apply that. It's just straightforward.
So the function that you are using to predict is always constant on training, yeah?
Always what?
It's constant on training, on the training points.
It's condition.
There is no randomness. Then, if you want to predict the label for a training point, it is always, there is no variance for that. Just the variance is set 0.
It's not necessary. It's possible have 0. Have a
Because during the okay.
Yeah, I think your question is really good. I don't want to go that in depth, but I can tell you, if your noise is 0, then you should that. I mean, if your sigma square is 0, mean that your training data doesn't have any noise variance. Well, yeah, indeed, it's positive variance is 0. Otherwise, it is not. If you can see it by looking at this. If a sigma square is 0, then this guy is simply 0. But because the practical data, you always assume, okay, there's some kind of noises which corrupt ground truth function values. That's where your observation. So when you infer the posterior distribution of the ground truth function value, it is not necessary to overlap the observation. It has some like uncertainty there.
But it's more concentrated.
Yeah, much more concentrated on that. Other question? Okay, so just to give you a sense, the prior functions and the posterior functions. That gets to the point you mentioned. So here I want to mention that there is a tiny variance here, and but compared with other places, it's too small. It doesn't mean 0 variance. So how do we get this, right? This is actually computed by looking at fx star given the training data y, and from this formula. And you can see that in the prior space, because you can draw a lot of functions right from the prior, and the prior is quite flat. And this region, this shaded region, indicates the prior variance for each function value, right? But after you have observed like 2 training points, right? If you compute the posterior distribution according to this conditional Gaussian, right? And if you look at the posterior variance about the function values, it will give you this. So you can see that surrounding the training inputs, you are much more certain about function values, right? So you can see very, very small variance. However, when you move away from the training region, you get much more uncertain about training, about the function values. So have a large variance. That's the benefit of Gaussian process. It gives you not only the prediction, but also give you the variance. You can look at the variance and see if you really think you are confident about your prediction. Does it make sense? Okay. So now, I think the last point I want to talk about Gaussian process connection to Bayesian neural networks. This is a famous theorem, and the proof is really simple. So just to give a sketch to talk about the idea. Right? So actually, we can show that under certain prior distribution over the weights in a Bayesian neural network, and when the network width, when the width of network goes to infinity, then the output of neural network will converge to a Gaussian process. It's proven by Raphael, who is the pioneer in Bayesian statistics and Bayesian machine learning. Right? So how do we see that? Right? consider a neural network with only one hidden layer. Like, actually, this can be generalized to multiple layers. Just if we just consider one hidden layer, and we denote the weight vector on each edge by u1 to um. Like that means your width of your hidden layer is m. Right? You have m neurons. We know that the output or the value of each neuron in this hidden layer is actually some nonlinear transformation after linear transformation UG transpose X. That's the definition of the neural network. We apply sigma or whatever tanh, whatever activation function. And then you just do a linear combination of these neurons in the hidden layer to get the output f of x. Right? So your f of x is a function of x, and now it's parameterized by neural network. It's parameterized by u1, u2 to um, parameterized by the weights on the last layer, right? We want to, yeah. Is everyone comfortable? This is our basic setting. So now, and of course, this sigmoid can be any activation, continuous activation functions, tanh, sigmoid, etc. Right? So now, we assign, because we're constructing Bayesian neural network, right? We can assign to each weight vector on the hidden layer with some prior, right? But with the same prior with some bounded variance. So the bounded variance is just important for you to show the convergence guarantees, right? But it's pretty flexible, right? You just want to assign some prior. It's not necessarily Gaussian. It can be any other prior, as long as you have variance. Right? You have variance. Your variance couldn't be infinity. And then we assign each VG. That means the weights in the upper layer as the same prior with mean 0 and variance omega square over m. So basically, the larger the m, the larger the y's, the smaller the variance. This is our specially designed prior over the weights we want to em in the last layer. Okay? And we just require, okay, the mean is 0 and variance is omega squared over m. Okay. So now we can prove that if we take m to be infinity, meaning that you take these y's to be infinity, then your function, the output of neural network, which is a function of x, right, will follow a Gaussian process prior. In other words, it can be viewed as sampled from some Gaussian process. How do we see this point? Right? So if we look at the output of each neuron in the hidden layer, right, and because the associated weight vector like uj, like u1 to um, they have the same prior, right? So we know that this hidden output are all IID, right? Identically independent distributed, right? And then we can construct a bunch of values. This is just for convenience for the proof in the next step, right? We just multiply square root of m times v1 times h1x. v1 is actually the corresponding weight in upper layer. So remember, our final output of neural network is just the summation of this vg, hj, right? So now we just multiply each term by this square root m. And because these uj's are independent and following the same prior, each v, v1, v2 to vm are independent from prior. So when you multiply them together, we know that they're IID, right? They're identically distributed, independent with zero mean and some constant variance, as we just mentioned, because the prior u1 has bounded variance, and v1 has like specific variance, doesn't have a is bounded, right? So they have a constant variance. Then if you look at f of x, it is essentially the average of this m values, right, times square root m, right? So this is consistent with the definition here, right? The only difference is that, okay, because I multiply square root m here, right? I'm gonna multiply 1 over m and times square root so that I can cancel m out, right? So to recover the form, right? But if you look at it this way, right? If you look at the structure of fx in this way, because these guys are RID random variables, right? And according to the central limit theory, if you skew an average of a set of RID variables by the square root of the number of the variables you average, then you take the number of variables you average to infinity, then this variable, this average skewed average RID variables will follow a Gaussian distribution. That's just simple application of the central limit theory. And this is readily generated by an arbitrary finite set of inputs x1 to xn. So you can view like fx1 to fxn. You can join to look at them, right, as a vector. Well, they're going to still be a linear combination of vj and hj, x1 to xm, right? And the only difference is that, okay, each aj now becomes a vector, but they're still RID, right? You can still construct such terms and then view them as a skewed average of the RID random vectors, right? So that means you can still apply the central limit theory and showing that when m goes to infinity, this n outputs will follow a multivariate Gaussian distribution, right? So this holds for any finite set of inputs, meaning that any finite set of neural network outputs, when m goes to infinity, will follow a joint Gaussian distribution. That means f itself as a function of x is a Gaussian process. That's how I show that. It's very simple, but it's very profound. Okay. That means f follows a GP prime. Okay? So this theorem can be extended to multi-layer neural network, or in other words, deep neural networks. And in our paper 2017, they show that if you have like multiple neural network and then each layer, when their wise goes to infinity, then corresponds to deep Gaussian process, and they have some form to write down the covariance function in terms of this neural network. Okay, any question? Okay. Yeah, I think that's all about the Gaussian process regression we want to discuss. So in summary, Gaussian process is a very powerful non-parametric model for function estimation. The biggest benefit is that Gaussian process does not need to specify what's the parameterized form for that, right? Or you can alternatively view Gaussian process is actually a linear function of some very high-dimensional nonlinear feature mapping of the feature vectors, right? You have different views on that, right? And Gaussian process is convenient in that we can use a closed form to compute the predicted distribution. It's simply a conditional Gaussian, right? And it has also the profound connections to Bayesian neural networks. That basically says, okay, so don't look down upon Gaussian process. They're actually as powerful as neural networks. Any question regarding Gaussian process?
What part of Gaussian process is the most computational? What's that Gaussian process? Because I think network takes a lot of compute time.
Yeah, the Gaussian. Yeah, that's a good question. Yeah, I didn't mention that, but Indeed, Gaussian process, the bottleneck is the computation, as we mentioned. The reason is that, remember, if you want to maximize the likelihood, right? You have to maximize this multivariate Gaussian. This covariance matrix can be very large. Like if you have like 1 million training points, training data, right? You have 1 million function values. The covariance will be 1 million by 1 million. And it's very hard to compute that.
So the disadvantage of Gaussian process, it doesn't work well with a large data set.
I wouldn't say it work well. It doesn't work. It can work. It can work well as long as you can compute it. Yeah.
So it's very hard to train.
It's very hard to train for a large data set. But there have been a lot of like sparse approximations, low rank approximations to compute that. And recently there's some ways to, like for some special cases, you can convert Gaussian process to a stochastic differential equation. You can convert to the state space model, which is Markov chain, and you don't need any sparse approximations. But I mean, regarding computation of Gaussian process is a giant topic. Okay, I think we haven't finished up the Gaussian process. We got 5 minutes. I think I'm gonna I think I only want to use one slide to give us a summary of what we have discussed throughout the semester, right? So just this slides will be enough, I think. So basically throughout this semester, we're actually talking about 3 components in probabilistic machine learning, right? The first component, of course, is foundation, right? We spent a few weeks talking about that because it's really, I mean, probabilistic learning is not like other machine learning. It's not like as easy as ABC. You do need to know some fundamental concepts, mostly from the Bayesian statistics, right? You need to know what is MLE, what is type 2 MLE, what is Bayesian decision theory, calculate prior uniformity, prior exponential family, all kinds of stuff, right? Because they form the basic ingredients with which we can construct our models. And then the second component is actually about modeling, right? How we formulate a probabilistic model, right? We actually have many tools, right? We have a family of generalized linear models. We have graphical models, right? We can have a marriage between the graph theory and probabilistics to have this tool to construct a model. We can use neural networks, right? And we can use non-parametric model like Gaussian process, right? So from modern perspective, we have a variety of probabilistic tools to model whatever complex phenomenon you are interested in. But the model itself is not sufficient. Right? You have to be able to compute, meaning that given your data, you should be able to train a model. You should be able to predict at the new inputs, right? That's actually a key task of machine learning. But this is also a critical challenge in machine learning, in probabilistic learning, because if you want to compute the posterior distribution, it's usually infeasible. That means you have to resort to various approximate inference techniques, right? We talked about Laplace approximation, we talk about variational inference, we talk about Markov chain Monte Carlo sample, right? So basically, you can view like all kinds of current probabilistic learning techniques are inherited from these categories, right? So, and you're gonna synergize, if you're a practitioner of the probabilistic learning, you're gonna synergize the modeling and computation. Right? Sometimes you have to trade off between the two. You can't make your model too complicated so that the computation is too hard. Right? You have to make trade-off. Right? So in a nutshell, probabilistic learning is a branch of machine learning that uses probabilistic principles for model design and algorithm development. It is very, I would jump to the last slides. It's a huge branch of machine learning. Right? Probabilistic learning is a huge branch of machine learning. Due to the time limit, throughout this semester, we can only introduce the most important concepts and ideas. Hopefully, can give you some kind of sense about that, and it will help you if you really want to study in depth in the future, right? And my understanding of probabilistic learning is that it's promising in model, yet challenging in computation. So it is an elegant marriage of math and engineering, right? So some people, like when they just met me, I mean, in my area, they said, okay, you're doing serious, you're a theoretical guy. You're doing serious stuff. I said, actually, I'm not. I'm doing kind of like in the middle between the theory and applications. I'm not doing purely applications, because if you want to specify a probabilistic model, you do need a lot of mathematics. Even a computation, you have to involve a lot of mathematical operations, computations, all stuff. That makes your work looks very, very theory, but it's not that theory, because we still want our model to work. We want to give our task accurate prediction and also reasonable uncertainty quantification. Right? And it's hot in research, and it has growing attention in industry, because industry, the uncertainty quantification is really important. And as the progress of computation technique, people find out, okay, some probabilistic learning technique can be used, and they're gonna use that, right? And right now there are more and more general libraries are developed for convenient usage, like TensorFlow probabilistic library, PyTorch probabilistic library, like PYM, CMC. It's kind of general libraries to implement all kinds of Markov chain sampling for you, right? And black box variational inference, right? So hopefully, in the future, if you want to use some tools, you don't need to reinvent your wheels. You can first search for the web to look at those useful tools, right? So finally, and thanks for your efforts. I know this course is a bit challenging for some of you guys, and I thank your efforts and commitment to this class, and I wish you sincerely a great success in the future. All right. Next. And we stop here.
Professor, so if you want to learn more about this field, what are the next steps? Like, would you be able to provide us some direction or good books or papers?
I wouldn't provide some books, because all the books, existing books, are too thick. I mean, too much, and it's not systematic. I think reading the PRML book, plus, you have gone through this class, it should be sufficient. You should do it. If you really want to do this kind of research, you should do it right now. Don't need to, if you have something like you feel